Friends, welcome to the 30th lecture titled Marine Risers under Vortex Induced Motion. In the last lecture, we are discussing about the governing equations for estimating the motion response of marine risers. We also discussed about varieties of marine risers which are used for offshore application. We will continue with the discussion on motion response analysis of marine riser. Then we will look into a specific special application of marine riser under vortex induced motion in this lecture. We continue with the discussion on marine riser motion analysis. Let us say we have an elemental strip which is at an angle theta and strip angle about d theta. So, the forces acting on this at any center point S can be Fxs, Fts, Fw and Fys as we mentioned yesterday. There will be incremental force variation between the left and right boundaries of the strip. Let us say this is going to be Fa minus dFA by 2, whereas this is going to be Fa plus dFA by 2. Similarly, look at the moment, this is going to be Mb minus dMb by 2, whereas this is going to be Mb plus dMb by 2. Similarly, this is going to be Fs minus dFs by 2, whereas this value will be Fs plus dFs by 2. Then the center value is radius of curvature of the strip. Theta actually measures to the center, this is theta. So, therefore, the equation equilibrium in horizontal vertical and angular directions was discussed in the last lecture. We will continue with that now. We know that sigma Fy 0 will lead to F1 cos theta minus F2 sin theta minus Fw plus Fys. Let us set this to 0. Sigma Fx 0 will lead to F1 sin theta plus F2 cos theta plus Fxs minus Mx double dot set to 0, where M is the mass per unit length of the segment considered, and sigma m 0 will yield to dmb by ds. plus Fs will be 0, where F1 is dFA by ds minus Fs d theta by ds, and F2 is dFs by ds plus dFA plus Fa d theta by ds. Let us say this is equation 1, equation 2. Since deflections of the riser are small, we can apply the small deflection beam theory. Also, we know from the geometry cos theta is dx by ds and sin theta is dy by ds. Therefore, MB, which is actually EI d theta by ds, can be expressed as EI d square x by ds square, equation 3. So, therefore, now the first equation, set of equation will now turn to dFA by dy minus d by dy of Fs dx by dy minus Fw plus Fys is 0. Similarly, sigma Fx0 equation will turn out to be d by dA of Fa dx by dy plus dFs by dy plus Fxs minus mx double dot is 0. The third equation, which is sigma m0, will turn out to be d by dy of Ei d square x by ds square plus Fs is set to 0. I call this equation number 4. Now, I want to write equation of motion of the riser in the horizontal plane. As we said in the last lecture, one can write this in any plane, but we are interested in writing in the plane where the motion response of the platform is captured. So, we will do it in the horizontal plane. This can be obtained by summing up the above equations, or let us say by combining the above equations. When you combine them, it simplifies to secant theta d square by ds square Ei d theta by ds minus Fa d theta by ds minus Fw minus Fys tan theta plus mx double dot will lead to Fxs. We call this equation number 5. Let Ai and A0 be the internal and external area of cross sections of the riser. Interestingly, the internal segment will be under hydrostatic load pressure. Because the internal fluid which is flowing through the riser will oppose the hydrostatic load arising from the external fluid. Therefore, we should look for a static equivalent pressure, which is given by F x p A 0 P 0 minus A I P I external minus internal of d square x by dy square minus A 0 P 0 minus A I P I of dx by dy, equation number 6. Therefore, the equation of motion which is shown in equation 5 is now modified, which will be d square y dx square of E I dy square minus F A plus A 0 P 0 minus A I P I of d square x by dy square minus rho s g A 0 minus A I minus F y s minus g times of A 0 P 0 minus A I P I the whole by dx by dy plus of course m x double dot will now deal with f x s, equation number 7, which is the modified form of equation 5. Now, in this equation, this particular term is called as effective tension, which is referred as F effective in the literature. Hence, let us rewrite this equation as d square by dy square of E I a function of y x by dy square minus d by dy of F E, that is an effective tension of dx by dy plus m mass per unit length, which is also a function of y x double dot, can be now said as f x s of x, y and t. Now, the one what you see here in equation 8 is the equation of motion for the riser under the given set of loads. In this equation, the first term represents the resistance of the riser due to its flexural rigidity. You can very well see here the E I term accounts for this. The second term in the above equation refers to the load from the axial force, essentially the tensile force, what otherwise we call as top tension, and the external internal fluid pressure. The third term in the above equation is the internal resistance of the riser segment. The right hand side of this equation needs some special attention, which is f x s of x, y and t. The right hand side of this equation represents the applied horizontal force on the riser. So, very importantly, the basic assumption here is riser inertia force is absent, because we are looking for a simplified static analysis. Therefore, equation now reduces to d square by dy square E I function of y d square x by dy square minus d by dy of f equivalent of y dx by dy plus my of x double dot is some value on the right hand side. I call this as equation number 8a, it is a modified form. Now, the right hand side of this equation of motion is given by half rho, which is the applied horizontal force, C D, which is again a function of y, diameter again a function of y, u y and u y, where u y is the current velocity which is a function of the vertical coordinate y. Of course, C D of y is the drag coefficient, which is again a function of y. Equation number 9. So, friends, when the marine riser is subjected to the loads as shown in the segmental length, it undergoes various special set of responses. The set of responses what the marine riser undergoes is of a special interest. This essentially induces what we call as flow induced vibration, or sometimes referred as vortex induced vibration. Essentially, this is a characteristic of flow induced motion, what we call as FIM. So, this results in formation of vortex, which arise or originate from the surface of the structure. This occurs mainly due to the fluid past the structure, When risers are exposed to fluid flow, flow separation takes place. For example, the surface, let us try to plot the variation of flow as various locations. Let us say at the point P, and at the point S. From this point onwards, you will notice that there is a separation takes place, and because of the separation, the flow characteristics will vary. Similarly, at this point, it initiates what we call recirculation. So, boundary layer separation takes place, and the pressure distribution shows there is a clear separation. So, this may result in what is called vortex formation. Schematically, if the body which is kept in the flow field obstructs the flow pattern causes rotation like this, which forms vortex shedding. Now, the consequences of vortex shedding. What will happen when vortex induced vibration is generated? The vortex shedding frequencies tries to lock in with the natural frequency of the riser. This will lead to a resonating condition. So, the flow separation which has taken place as the fluid passes the body results in formation of vortex which is trailing behind the body. So, VAV is caused by the vortex which is shed behind the body in the fluid flow. Now, let us ask the question, what would be the consequences if VAV is formed? They can cause alternating pressure field. On the surface of the riser. This can result in oscillating lift and drag forces. That is a very important consequence. In case of unsteady flow, when the vortex shedding frequency matches, or I should say even when approaches the structural frequency, the structure undergoes what we call vortex induced vibration. So, the serious consequence of VAV is it will introduce what we call something a lock-in phenomenon. So, at the lock-in phenomena, at this stage the vortex induced vibration frequency will be more or less closer to the natural frequency of the structure, which will cause large cross flow. So, that is another consequence we have. So, this can result in a fatigue damage, it can result in reduction of life of the structure, system. This can induce large transverse motion. That is a very serious consequence we have, because in such vibration inductions failure can occur very easily even at a low amplitude of vibration in transverse motion. Many mooring lines or cable stayed bridges have been analyzed for this. One important failure is the Tacoma bridge, which has failed in one of such consequences. So, large transverse motion initiation is a major drawback when VAV is induced in the system. It can cause operational difficulties, the operability of the platform can be challenged, and it can cause excessive vibrations, which can result in seasickness. So, that can be one of the consequences on human on board. So, people have studied these consequences and this kind of responses very widely in the literature. Researchers state VIV are actually are the result of additional exciting forces that are generated by vortex shedding on the bluff body. This motion response can be captured as people have indicated. This is very clearly said by Sarabkaya in 1979. If you want to capture vortex induced vibration response range, one need to include the reduced velocity value which corresponds to inverse of Stokal number as said very clearly by Bierman 1984. People have also proposed various suppression systems. For controlling such responses. For example, Blevins 1994, Kalak et al. 1991 and Farrell at 2007 proposed many suppression systems which are helpful in controlling such responses caused by vortex induced vibration, essentially on offshore cylindrical members. Keeping this in mind, let us discuss quickly a case study example to illustrate the effect of suppression systems on vortex induced vibration on a given offshore cylinder. An experimental study was designed to examine this. The left hand side shows the line diagram of the study. A cylindrical member is suspended from a spring, from a support, and there is an horizontal shaft which holds the cylinder by means of rollers. The full setup in a 3-dimensional view is shown in the photograph here, which is the setup assembly. The model dimensions as indicated here are the diameter of the cylinder, the thickness of the cylinder, the length of the member which has got a draft of about 917, and then the rest is of a clear height. The vortex induced motion generally can be characterized by different dimensionless parameters for example, Reynolds number, rho u d by mu, the Strohal's number d by u, the reduced velocity which is very necessary to estimate the response, which is ut by d, and then the amplitude ratio, which is A by d, where d is the diameter of the cylinder, u is the current velocity under study, t is the time period of the structure. Let us say in my case the cylinder, Fs is the vortex shedding frequency, A is the motion amplitude, rho density of fluid, and mu the dynamic viscosity. Let us quickly see the experimental setup which is assembled to conduct the response study. You can see the cylinder suspended from the arrangement, held down by a spring, is now attached to the moving carriage. This carriage is going to move with a specific velocity in the fluid medium, which is essentially water. This is the immersion of the cylinder. You can see the cylinder here. The safety clamps will hold down the cylinder to the assembly, and LVDT is being used to measure the response of the cylinder in the transverse direction, and now this is attached to the assembly and the carriage is going to move, where we are going to measure the response of the cylinder under the vortex induced motion. Interestingly, before we look at the test results and conclusions, let us try to look at this figure where the relationship between the Stokes number and Reynolds number for a circular cylinder is indicated. One can very clearly see here, for the range of Reynolds number varying from 25,000 to 150,000, the Stokes number remains almost constant at 0.2. So, this is the range where the study can be now carried out. So, the maximum amplitude is expected at reduced velocity of 1 by s, which is actually equal to phi. The reduced velocity of phi means that 0.73 meter per second is the appropriate value which we are looking for. So, as said by Biermann in 1984, which is Biermann PW 1984, vortex shedding from oscillating bluff bodies, annual review of fluid mechanics, volume 16, 195 to 22, says that the reduced velocity at which the VAV can be captured is inversely proportional to the Stokes number. So, that is why we said is 1 by s, and the maximum amplitude is attained closer to this value, but not at this value. That is very important. Let us quickly discuss very briefly the experimental procedure. The cylinder is fixed to the setup. The setup is clamped to the towing carriage. Tests are carried out in the velocity range .2 to 1.2 meter per second at an interval of 0.02 meter per second. It is very interesting to note that the test section is moved and water body or the fluid medium is kept stationary. LVDT, which measures the response, receives supply from a 12 volt DC supply. Oscilloscopes are used to record the response. I should say response history. All tests are conducted with a specific mass ratio of unity. The mass ratio is actually the ratio of mass of the system to the buoyancy. The photograph on the left hand side shows the flow of water when the carriage moves. You can see here very interestingly the shedding frequency happens at the trailing side of the cylinder on the surface, where the flow separation is expected to take place. The right hand side picture shows very clearly the cross section view of the cylinder with a spring attached to the cylinder. The equipment used, the oscilloscope and the data recorder used for sensing and data processing, is shown on the screen now. The screen now shows the time series or time history in seconds of the peak transverse oscillation, which is now recorded at reduced velocity 5.44 at 0.8 meter per second. We have also plotted the amplitude ratio of the cylinder without any suppression for different velocities. The reduced velocity of different range is shown in the x axis, and on the y axis shows the amplitude ratio for a bare cylinder which does not have any proposed suppression systems for controlling the vortex induced vibration. It very clearly shows by comparing the different plots that following observations can be recorded on a bare cylinder. Response increases, reaches the peak and then decreases. Very interestingly, a lock-in phenomena is observed at reduced velocity of 5. The maximum amplitude ratio of 0.87 is seen, which indicates about 87% of displacement with respect to the cylinder diameter, because A by D is about 0.87, where A is amplitude ratio. Then suppression systems are proposed. It is interestingly seen that VAV suppression can be achieved by surface protrusions, by putting helical strikes, etc. Examples: helical strikes, but of course this will increase the drag. One can also use helical wires, helically wound around the body, so both studies are carried out, like vertical wires and helical strips. So, essentially vertical wires are attached to the body at different positions. Helical wires are also attached. So, two set of studies are conducted. If you look at the cylinder diameter, helical wires are attached at different angles. This is one of the variable used in the study, alpha, and this is indicated as L, and this is my flow direction. If you look at the elevation, the suspended cylinder has got wires for the entire length. So, for alpha being 40, L becomes 0.44 d. For alpha 50, L is 0.55 d, alpha 60 0.67 d, alpha 70 L becomes 0.78 d, and alpha 80 degrees L becomes 0.89 d, for which the tests have been conducted. Now, the response plots have been obtained. We can now compare these response plots as shown in the figure for different values of alpha. So, 0.55 d, if we change it to 0.67 d, then further at 0.78 d and 0.89 d. So, there are different plots now superimposed for different values of L, and the dark line, what you see here, the dark line, this shows the response of the cylinder without any suppression system, what we call as a bare cylinder. So, interestingly, from the curves one can see that the maximum suppression is seen when the tripping wires, nothing but the vertical wires, are attached at 50 degrees. In this case, the response is reduced by about 71% when compared with the bare cylinder. The next study was with the helical strikes at 3 different points on the surface equivalent at 60 degrees. The wires are connected and they are helically wound at different pitch, 5 times the diameter, 7 times the diameter and 10 times the diameter, and the wires are placed symmetrically with respect to the wave direction for the cylinder as shown in the figure here. Let us compare the responses of the helically wound cylinder for different pitch ratio as 5D, which is seen in the screen here, for 7D and for 10D. So, the plots are now compared for different pitch of the helical strakes or the wires which are wound on the surface of the cylinder at different pitch values. So, now they are superimposed and compared with the bare cylinder. The plot what you see here with the black square filled in is for the bare cylinder, whereas other plots are shown for the helical wires wound around the cylinder. One can very clearly see this gives a very effective suppression of the response of the cylinder at various reduced velocity ranges for different amplitude ratio as seen in the curve. So, by comparing these plots, one can now see for helical wires placed at different pitch, but at an angle of 60 degree, which was found to be effective from the previous study, which was 50 degrees, it is seen that the maximum suppression is recorded at a pitch of 10D, where the area is reduced by about 40%. It is also seen that all the plots with helical wires follow a similar trend. Okay. This is essentially due to the omnidirectional property achieved by laying the wire at 60 degree inclination at different pitch angles. So, friends, in this lecture we have seen how to derive the governing equation of motion for a riser under the environmental loads acting on the riser. We also try to understand the equation of motion governing the response of the riser. We have also understood what would be the vortex induced motion and their consequences on the riser configurations. We picked up a case study to examine the suppression systems which are caused the reduction in response at different reduced velocity at different range of Stokes and Reynolds numbers. We said that the experimental studies discussed show that tripping wires are effective in VAV suppression, vertical wires placed at 0.55 D apart and 0.67 D apart found to be effective. For the helical strikes or the helical wires placed around the body, it is seen that for a pitch of 10 times the diameter, the response suppression, or I should say the response reduction, is seen to be maximum. The study has got interesting references which can be seen from the list of references in the NPTEL website of this course. So, interestingly, in this lecture we learnt how to examine and understand the suppression systems under VAV responses, which has got very serious consequences on marine risers. Hope this experimental study shown to you will intuit you to examine such more detailed analysis with more experimental, numerical and analytical investigations on marine risers, because these are special kind of responses induced on offshore systems under the fluid flow. Thank you very much.